Welcome to your deep dive. Today we're leaving the typical silicon and circuits behind, going a little more mechanical with our computing.
Yeah, you're right. It's not your typical subject. We're diving into a collection of journal articles, research papers, all about mechanical computing.
And I gotta say, I'm kind of hooked on this idea already. Gears and levers, crunching numbers instead of microchips. That's surprisingly intriguing, but it's more than just steampunk
Oh,
aesthetics.
absolutely not. See, mechanical computing, it offers some unique advantages,
Mhm.
especially in situations where electronics, they just wouldn't last.
So you're saying my laptop wouldn't survive a trip to, like,
Wow.
Venus?
Probably not very long, no. But a mechanical system, if it's designed right with the right materials, it can handle those conditions, no problem.
Now that's some next level durability right there. Okay,
Thanks.
I'm also really curious about this whole energy efficiency thing. The sources mentioned some pretty incredible potential savings.
Rightfully so. Think about it. In a traditional computer, all those electrons moving around, it takes a lot of energy. Mechanical computing, especially at the molecular level, could use drastically less energy. We're taking moving atoms and molecules instead.
Okay, so then how does a computer powered by, say, a few molecules even work?
It's still early days, but the concept is fascinating. Imagine you could design molecules to act like gears, levers, switches, all working together to represent and process information. It's a tiny machine at the nanoscale.
I'll admit, I'm having a little trouble picturing that. So can we trace this idea back at all? Like, historically, is there a connection from gears to the smartphones we have today? It seems like a huge jump.
More like a continuous thread than a jump, really. Think
Right.
about Charles Babbage's difference engine. This was the 1800s, long before spreadsheets or even calculators. Back then, people needed complex mathematical tables for, well, everything. Navigation, engineering,
And those were calculated by hand.
but for hand, yeah, and full of errors because of it. Babbage, he wanted to automate that process, get rid of the errors, speed things up.
So Babbage was essentially trying to build an analog computer, kind of.
In a way, yes. But funding was an issue, and the technology just wasn't there yet. So his difference engine, it was never actually finished. But the designs themselves, even the parts that were built, they were incredibly advanced for their time.
It's always amazing to think about those early pioneers laying the groundwork for the tech we take for granted. But were there any success stories back then, like any mechanical computers that actually worked?
Oh, definitely. One of the best examples is Herman Hollerith's tabulating machine. Revolutionized the 1890 U.S. Census it did.
The census.
This machine, it used punch cards to process all that data. Millions of data points, each one a hole punched in a specific spot on a card.
So almost like a physical version of the ones and zeros computers use now?
That's a really good way to put it.
Yeah.
And Hollerith's machine, it cut the time to process the census way down. It proved that mechanical computing could have real-world uses, and it paved the way for how we process data even today.
So that's complex tables to processing entire censuses, all with mechanical systems. Sounds like this type of computing had a pretty wide range back then. Speaking of which, those bomb site computers used in World War II, weren't those mechanical too?
They were, and talk about pressure. These machines, they were vital for navigation and targeting. Had to be compact, precise, and function perfectly in the most demanding conditions imaginable.
High stakes. It's kind of mind-blowing that something so critical relied on gears and moving parts. How could they be that reliable?
That's a testament to the engineers who designed them, built to last and to perform, no matter what. They make you think twice about what a computer can be, that's for sure.
It seems like there's a huge range then when we're talking mechanical computing, from these big, almost clunky machines to the potential of computing on the molecular level.
You're spot on. The principles of mechanical computing, they work at all sorts of sizes. We've talked about the big picture, the macroscopic, but things get really interesting when you go smaller,
Yes.
into the microscopic.
The realm of MEMS. MEMS. Okay, you've got me there. I'm not familiar with that one.
MEMS stands for micro-electromechanical systems. Basically, imagine tiny machines, often made using the same kind of processes as computer chips, but with moving parts. Microscopic gears, levers, sensors. They bridge the gap between those large-scale computers we talked about and the molecular level.
So like shrinking those historical examples down to a microscopic scale?
Exactly. And at that size, things get really exciting. Researchers have actually managed to create logic gates, the building blocks of computers, but using MEMS. So we're talking microscopic mechanical parts instead of electronics.
Instead of electrical signals, we have tiny gears and levers flipping to represent ones and zeros. That's wild. That is a totally different way of thinking about computing than I'm used to.
That's exactly it. But let's go even smaller. back down to the molecular level. If we can get this to work, if we can use individual molecules as building blocks, the potential benefits are huge.
Okay, so we're talking computers millions of times more powerful, all packed into like a grate of sand. It's kind of hard to wrap my head around.
It really pushes the limits of what we think is possible. And we're not quite there yet, but researchers are already working on molecular scale mechanical logic gates. Imagine the energy efficiency.
You keep mentioning energy efficiency, and I get it, moving molecules around is going to take way less energy than pushing electrons through circuits. But, like, how much more efficient are we talking? Can you give me a real-world example?
Imagine a molecular computer. It can do billions of calculations using the same energy it takes to blink your eye. That's the kind of efficiency we're talking about.
Hmm.
Our computers now, they just can't compete with that.
That's incredible, but I have to imagine getting something like that to actually work. There have to be some serious roadblocks. What are the biggest challenges with molecular mechanical computing?
One of the biggest ones, and it's funny because we don't even think about it at larger scales, is friction.
Friction. How does friction even work with something like a molecule-sized gear?
Even at that scale, friction exists. Think about it. These unbelievably tiny gears, designed atom by atom, they could stop working completely just because of those forces we never even notice in our daily lives. Overcoming that, that's a huge challenge.
It's like you're trying to build a perfectly oiled machine, but at the atomic level. That's got to be unbelievably complex.
It definitely comes with its own unique challenges, yeah. And then there's the whole manufacturing side of things, fabrication at the molecular level. That requires a whole new approach. We're not talking about assembly lines here. We need techniques that can actually pick up and assemble individual molecules with atomic precision.
Like a pair of tweezers for atoms. It's mind-boggling. But, okay, before we get too far into the future, I want to take a step back. Something a little more, well, down to earth. Can you walk me through how a mechanical system actually calculates something? Like a real example.
Let's go back to the slide rule. Seems like a simple tool, but it's a really elegant example of mechanical computing in action. Remember those logarithmic scales?
Refresh my memory on how those work.
Basically, a logarithmic scale, it uses distances to represent the logarithms of numbers. So when you slide one scale against the other, what you're really doing is adding or subtracting those distances, which directly translates to multiplying or dividing the original numbers.
You're physically moving these parts, and that's doing the math for you. That's incredible. It's like a mechanical calculator.
Exactly. A perfect example of how moving something physically can be a calculation in itself.
That's so cool. And people used to use those for, like, everything, right? Really shows you how far we've come. But you mentioned how mechanical computing works at all these different sizes. We've talked about the big, the small, but there's that middle ground too, right? The MEMS scale. Any examples of how a MEMS device could be used for computation?
As a matter of fact, one of the papers we have, MechComp links and joints.pdf, it proposes a model for a completely mechanical computer. It's built entirely out of links and rotary joints, like a crazy, complicated erector set.
Okay, I have to admit that sounds kind of intimidating and fascinating. But how would something like that even work? How does it compute?
It all comes down to these things called locks and balances. Imagine like a four-bar linkage, the kind of mechanism you might find in a car's suspension. Basically, a parallelogram made of these rigid links connected by joints that let them pivot. Now, try to stick another link in the middle of that parallelogram, a link that's the wrong size or at a weird angle. The whole thing will lock up. It can't move.
Like throwing a wrench in the gears?
Kinda, yeah. And that's how the locks work in this model. They either allow movement or prevent it, depending on how those links are set up. Balances, on the other hand, they're more like levers. They can take the movement from the locks, amplify it, redirect it, things like that.
Okay, I think I'm starting to see how this could be used for computation. It's like one part moves and that triggers a whole chain reaction, right?
Exactly, like a domino effect.
Yeah.
And by putting these locks and balances together in the right way, you can actually create logical circuits. The paper even shows a design for a mechanical NAND gate using this system.
A NAND gate. Isn't that one of the, like, core parts of how computers work today?
It is. And this model proves that you can get that same functionality, but mechanically. No electronics required.
That's amazing. So design the arrangement of these links and joints carefully enough, and you've got the basic functions of a computer. What would be the advantage of building it this way, though?
Well, as we've talked about, energy efficiency is a big one. This kind of mechanical computer wouldn't need a constant flow of electricity like our computers today. Theoretically, it could run for a long time on just a little bit of power, maybe even power it harvests itself from the environment.
A computer that's both energy efficient and super durable. That's huge for like extreme environments. I do have to wonder though, this system with all its moving parts and stuff, wouldn't it be a lot slower than our electronic computers?
That's true. Mechanical systems, they do tend to be slower than electronic ones. That's just the nature of how they work. Electrons are fast. Even the best mechanical parts, they're limited by the laws of physics. But speed isn't everything, right?
Right, right. There's something kind of elegant about it though. This system, it's like a beautifully crafted clock, but for information instead of time.
It's definitely a different way of thinking about computation, and that might be one of the most valuable things about mechanical computing. It makes us rethink this fundamental connection between information and the physical world.
It's true, we think of information as this like intangible thing, something that only exists in the digital world.
Exactly. But then you have mechanical computing, which is all about encoding and processing information in a physical form. It challenges what we think a computer can be.
And who knows what other ways of computing are out there just waiting to be found. It's like
Yeah.
we kind of forgot that mechanics can do amazing things with information just because we're so used to the digital world now.
Right. It reminds us that there are all these different ways to achieve the same thing, even in something as complex as computing.
Makes you wonder, what other innovations are we missing out on just because we haven't connected the physical and digital worlds yet? But okay, back to mechanical computing. We've talked about the upsides, but there have to be some downsides too, right?
Yeah.
Nothing's perfect.
Of course, there are always trade-offs. And one of the big ones with mechanical computing, we've kind of touched on it, is speed.
Yeah, that makes sense.
Mechanical systems are just naturally slower than electronics. Electrons, they move incredibly fast. But any mechanical part, no matter how well designed, it's bound by the laws of physics.
So no mechanical supercomputers anytime soon.
Not if we're thinking about it like we do now, no. But speed isn't the only thing that matters. If you need something durable, energy efficient, something that can survive in crazy environments, then that trade-off in speed, it might not matter as much. The right tool for the job, right?
Right. Makes sense. Every technology has its strengths and its weaknesses. But even with those limitations, mechanical computing could be huge for all sorts of fields, couldn't it?
Absolutely. Think about medicine, for example. Imagine a pacemaker that's powered by a mechanical system, much more durable, energy efficient. Or prosthetics that respond more naturally to movement because they're using those same mechanical principles.
That's a really cool way to think about it. Devices that work with the human body more seamlessly because they're designed like it.
Exactly. And that's just one area.
What about space? That has to be a perfect fit for this kind of technology.
Absolutely. Think about sending a probe to a planet with, like, extreme temperatures, the kind of radiation that would fry a normal computer instantly, but a mechanical one. That could be our key to gathering data in those places.
Exploring parts of the universe we couldn't reach before. All thanks to technology that takes us back to the very beginning of computing.
And that's what's so cool about mechanical computing. It's this bridge between the past and the future.
Yeah.
It's full of these contradictions, physical parts, but doing these complex calculations, applications that are both tiny and massive.
Mm.
It makes us rethink what a computer is, what it can do.
Like it's a reminder that sometimes the best innovations come from challenging those assumptions, looking at things in a new way.
That's it, exactly.
Yeah.
And if you take one thing away from this deep dive, I hope it's that. A sense of wonder about what's possible, and a little healthy skepticism next time someone says, that's just not how computers work.
Because as we've learned, there are tons of ways to compute. And the future of computing, it might be a lot more interesting and diverse than we think.
Couldn't have said it better myself.
This deep dive has really got me thinking. I'm looking at my phone in a whole new light. It's amazing, this potential for mechanical computing to change not just our tech, but how we understand information itself.
It's an exciting field, that's for sure.
It really is. Well, on that note, we'll leave you to ponder the gears and levers of the future. Join us next time for another deep dive where we'll explore a whole new topic and uncover even more fascinating insights.